Hi, my name's Andrew Jordan. I'm a junior chemistry major from Rochester, New York. I would like to mentor Dr. Moy's Chem 262003 lecture at 12:20 on Monday, Wednesday, Fridays. I would like to mentor because I'm very passionate about the material. I've loved organic chemistry and definitely see myself pursuing a career in STEM, maybe health sciences, research, organic chemistry, and just having those mentors, the student-to-student dialogue, and just seeing my classmates up there giving help and just talking back and forth on how to solve these problems was huge in terms of my success as a organic chemistry student. And that being said, I would like to do the same, and I would find enjoyment in doing it. Today, I'm just going to go over a moderately difficult synthesis problem. So right away, for an introductory organic chemistry 2 student, it might be daunting to look at that and think, well, what's going to be the first step in achieving that product? So what I would suggest is always the retrosynthesis method, and that becomes especially useful for me anyways on the more difficult problems. So right away we can see we have a substituted benzene with a straight chain alkyl group, and we have a primary alcohol, the primary alcohol as like our original reagent. So seeing the substituted benzene, we know it's going to be electrophilic aromatic substitution, and most commonly a Friedel-Crafts either acylation or alkylation. So a student may think, well, it looks like a straight chain alkyl group. We're just going to do a Friedel-Crafts alkylation, and what I'd counter that with is, well, that would be possible, but at the same time, more often than not, we're going to get rearrangements due to carbocation stability, and it's not going to get the product that we want the majority of the time. So that being said, when we see that straight chain alkyl group off the benzene, it's kind of dead giveaway that it's going to be a Friedel-Crafts acylation. So knowing that, the second to last step is going to be a substituted benzene with a ketone on it. And how do we do that? Well, that's easy. That's from a Friedel-Crafts acylation. Well, with a Friedel-Crafts acylation, you need AlCl3 and acyl chloride and benzene. So there we have the addition of benzene and AlCl3 listed down here. We have benzene and AlCl3 with the acyl chloride. Well, from here we have to think, well, how are we going to get the acyl chloride? Well, we know how to get an acyl chloride if we move backwards using a carboxylic acid and thionyl chloride. So that being said, we know that a step in the process is going to be having a carboxylic acid, turning that into a acyl chloride, and then doing a Friedel-Crafts acylation and reduction. So from there, all we have to look at is, well, how are we going to get a carboxylic acid from the original reagent? Well, that we can just use one of the more common oxidizing agents in organic chemistry. We can use chromic acid to turn that primary alcohol into a carboxylic acid. And reacting that carboxylic acid, we can generate these intermediate steps and eventually achieve our end product. So having outlined the steps in reverse, now the best way to do that is just to go backwards. Reverse your steps from the original product, and after kind of reversing our steps, we see that that's the correct order, and we double check our steps, and we can lay them out right up here. We have the chromic acid, we have thionyl chloride to turn it into an acyl chloride, and then we have benzene and AlCl3 for the Friedel-Crafts acylation, and then finally we have H2PDC to remove that ketone functional group, and we get the straight chain alkyl group. Thank you.